Hey everyone! Welcome test takers to the ultimate high-yield physics explainer. Think of this as your straightforward, no-nonsense cheat sheet designed specifically to help you absolutely conquer the RRB Technician Grade 1 exam. If you're looking to maximize your score and truly lock down those tricky physics fundamentals, well, you're in the exact right place. We're going to take this massive, intimidating syllabus and break it down into clear, highly testable chunks.
So here's our mission briefing for today. First, we'll build from the basic language of units. Then we set things in motion with mechanics, add some effort and energy through dynamics, dive into the invisible forces of thermal properties, and finally, wrap the whole thing up with a rapid-fire ultimate exam checklist.
All right, let's jump right into Section 1, Units, the language of physics.
Okay, so what you're looking at are the 7 independent SI-based quantities. These are literally the globally accepted foundation of all measurement. You can kind of think of these as the primary colors of physics, right? Everything else is just a combination of these 7. We've got the familiar ones, of course, length in meters, mass in kilograms, and time in seconds. But definitely don't forget the others: electric current in amperes, thermodynamic temperature in Kelvin, amount of substance in moles, and luminous intensity in candelas. Committing these 7 to memory is absolutely crucial, because the exam is definitely going to test your grasp on these foundations.
Now pay super close attention here because exams love, and I mean love, to test the 2 supplementary units. While those 7 base units cover physical quantities, we actually need these 2 to measure geometry and space. The plane angle is measured in radians. That's the standard 2D angle you're probably used to from trig. But when we expand out into 3-dimensional space, we get the solid angle, which is measured in steradians. Jot that down for sure. It's an easy point on the RRB exam that so many candidates just completely overlook.
Moving right along to Section 2, Mechanics, Matter, and Motion. This is where physics gets visible.
Highlight this next point in your mental notes. Mass and weight are entirely different beasts. I know we use them interchangeably in everyday life, but in physics, no way. Mass is this unchanging, intrinsic property of a body measured in kilograms. It's a scalar quantity, meaning it has magnitude but 0 direction. Weight, on the other hand, is the actual gravitational force pulling on that mass. Because it totally depends on gravity, weight is a vector force, measured in newtons, and it literally shifts depending on where you are. So your mass is exactly the same on Earth and the Moon, but your weight, drastically different.
This brings us to a classic exam trap involving density. Standard density is pretty straightforward. It's just mass divided by volume, usually kilograms per cubic meter. But then there's relative density, sometimes called specific gravity. This compares a substance's density directly to the density of water at 4 degrees Celsius. And here's the catch. Because you're dividing one density by another density, the units perfectly cancel each other out. That means relative density is purely a ratio. It has absolutely no unit at all. So when the exam asks for the unit of relative density, remember, it doesn't have one. Here's another vital distinction that trips up a ton of students: speed versus velocity. Speed merely measures how fast you cover distance, and it genuinely doesn't care about direction. It's a scalar quantity, always positive or 0. Velocity is its vector cousin. Velocity strictly tracks your precise directional displacement over time. Imagine running in a massive circle and ending up right back where you started. Your speed might have been incredibly high, but your overall velocity? Technically 0, because your final displacement is 0. Both are measured in meters per second, but that directional component changes the whole shebang.
Building directly on velocity, we have acceleration, which tracks how rapidly that velocity is changing. The formula is final velocity minus initial velocity, all divided by time, giving us meters per second squared. And keep in mind, since velocity is a vector, acceleration is a vector too. It can actually act in the exact opposite direction of motion, acting like a brake to slow an object down. In physics, we refer to this negative acceleration as retardation or deceleration.
Okay, take a mental snapshot right now, because mastering these 3 equations of motion for uniform acceleration is non-negotiable. First, v equals u plus at. Second, s equals ut plus 1/2 at squared. And third, v squared equals u squared plus 2as. Memorize these. Literally write them at the very top of your scratch paper the second you sit down for the test. They're basically the master keys to solving almost any kinematics problem they throw at you.
Let's shift gears now to Section 3, Dynamics, Work, Power, and Energy, removing from just observing motion to actually adding tangible effort into the mix.
This brings us to an absolute classic RRB exam scenario.
It's perfectly designed to test if you truly grasp the physics definition of work versus how we use the word normally. Picture a worker carrying super heavy luggage on his head, walking horizontally across a train platform. Ask yourself, according to the strict mathematical laws of physics, how much actual work is being done against gravity here?
The answer is 0. Crazy, right? It sounds completely counterintuitive because the worker is definitely sweating and putting in effort. But in physics, work equals force times displacement, times the cosine of the angle between them. Here, gravity is pointing straight down, but the walking displacement is purely horizontal. The angle between them is exactly 90 degrees. And since the cosine of 90 degrees is 0, the mathematical work done against gravity is a big fat 0.
This brilliantly illustrates the broader concept of energy, the sheer capacity to do work. Mechanical energy basically comes in 2 flavors. You've got kinetic energy, the energy of motion, and potential energy, which is stored energy based on position, like how high up something is. And the absolute beauty of physics is the law of conservation of energy. It states that energy cannot be created or destroyed, it merely changes forms. So whether energy is kinetic from motion or potential from position, the total mechanical energy in a conservative system stays perfectly, beautifully constant.
Now, if energy is the capacity to do work, power is how fast you actually pull it off. It's work divided by time, measured in watts. You'll also want to remember that 1 horsepower equals 746 watts. But here is the biggest trap of the section. Beware the kilowatt hour. Because it literally has the word watt in it, it sounds exactly like a unit of power. But it's not. A kilowatt hour is strictly a commercial unit of energy, representing 3.6 million joules. Seriously, do not let them trick you with that one.
Moving on to Section 4, Thermal Properties and Heat. Let's demystify these invisible forces.
A really fascinating and highly testable distinction to master here is the difference between heat and temperature. Again, we use them like they mean the same thing in normal conversation, but in science, totally distinct. Heat is the actual energy that's moving between systems because of a difference in their temperatures. It's measured in joules or calories. Temperature, though, is just a measurement of the average kinetic energy of the molecules inside a body. Put simply, temperature measures how frantically the molecules are vibrating, while heat is the energy transferring because of that vibration. Now, here's a surprising little fact about temperature conversion that exam writers absolutely love. You probably know the formulas to convert Celsius, Fahrenheit, and Kelvin. But did you know there's a specific magic number where 2 of these scales perfectly cross paths? Negative 40 degrees is the exact temperature where both the Celsius and Fahrenheit scales align. Minus 40 Celsius is exactly minus 40 Fahrenheit. Lock that number in. It's a super common trivia question.
Connecting this back to the real world, let's talk about specific heat and latent heat. Specific heat capacity is how much energy it takes to raise the temperature of a substance. Water has an incredibly high specific heat, which is exactly what makes it such an amazing coolant for car engines. It can absorb massive amounts of heat before actually getting hot itself. Then we have latent heat, which is the hidden energy required to change a substance's state, like boiling water into steam. This massive hidden energy of the latent heat of vaporization is exactly why a burn from steam is way more severe than a burn from boiling water at the exact same temperature. The steam is dumping all that extra hidden phase change energy directly into your skin.
And just like that, we've reached Section 5, the ultimate exam checklist. Let's lock all this in with a rapid-fire wrap-up.
This definitive checklist right here cleanly separates your scalar values from your vector forces. Remember, scalars like mass, speed, work, and energy only care about magnitude. Vectors like weight, velocity, acceleration, and force care about magnitude and direction. Take a mental screenshot of this. Knowing the difference between simple magnitudes and directional quantities on test day is going to save you points left and right.
As you head into your exam armed with the knowledge that gravity entirely dictates weight while mass stays stubbornly unchanged, I'm going to leave you with one final thought to chew on. If you were to travel to the exact center of the Earth, the gravitational pull from all the surrounding mass would perfectly cancel out, rendering your weight exactly 0. Yet your mass, the actual matter that makes you you, would remain completely intact. So what does true weightlessness reveal about the underlying nature of physics in our universe? Think about that as you continue your studies. Thank you so much for joining me for this explainer, and best of luck on your RRB Technician Grade 1 exam. You're going to crush it.